So you might have, geez, that's ugly. You might have recalled the linear time algorithm for determining whether a point is inside a polygon. And you might remember, or maybe you're just finding this out, that typically it's convention actually to store polygons in memory in terms of a counterclockwise ordering with respect to the points, so that the points are indexed in a manner that provides a counterclockwise turn if you were to kind of count them from one to another and make the polygon. So the reason why these two things are important, you'll see in a second. Let's just demonstrate what exactly is the relevance of this. And let's say that we have two triangles, and this point right here is 1, 0. Up here is 0, 1, and here is 0, negative 1. And pay attention particularly to this vector, which let's call it A, and this will be B, and this will be C. Now, let's make a determinant with A up here and B down here. So this will be 1, 0. This will be 0, 1. And you'll notice that this gives us a negative value. But if I change B to C, I switch them over, you'll notice that this gives us a positive value. Now, this is important because it turns out, and you can demonstrate and prove this quite easily using algebra, that if you have a vector, then determining what side a point is with respect to the direction of that vector is quite simple. You merely have to make another vector from the origin to that point, and then make the determinant, which is an artifact of the cross product. And if it's negative, it'll be on the left side. If it's positive, it'll be on the right side. So you might have an idea now. You can perhaps grasp that a linear time way to do this would simply be to make vectors from one point to the next on the polygon and ask the question, which is in constant time, is this vector, or is the point to the left of this vector for every point, for every line segment in the polygon? And so if the answer is yes to all of them, the point is definitely inside the polygon. We have to have a way to massively discard search space, because that's sort of the nature of logarithmic time complexity. You're massively discarding many potential search data points, let's call them, a large portion of the search space. Right? That's sort of the same thing in binary trees, which are a good visual example. Every time you search, you cut off an entire half of the tree over and over. Well, it's the same concept. So there's nothing that says that I cannot, for example, go over here and make a vector over here. So let's say that, well, we can make an equation and take advantage of iteration and say, well, we'll start these two vectors by setting this one as A. So we have A and B, and these are respective to the vectors they represent from the same origin, A and B. So this B will first equal 1, and this A will first equal n minus 1. Okay, so in that case we can make something like this, A plus B over 2. The ceiling of it is the next index we want to look at. So in this case, we have a polygon of 8 sides, and minus 1 is 7, B is 1, that is 8 divided by 2, it's 4, ceiling is still 4. So now we're looking at 4, index 4 over here, and we ask the question. And let's say that we have a point over here. Let's have 2 points. One is here, one is on the outside here, P prime and P. So, is it to the left? Well, no, it's not. So then everything here to the left could not possibly be a region in which the point could exist, because it's not to the left of this. And you can kind of imagine that this kind of cuts the plane into 2 partitions. So there's no reason to keep A over here. So we remove A and we say, well, since there's no reason to search over there, we're going to change A to this over here. So this is now A. Okay, fine. We just discarded all this search space. So we do the same thing with the other side. Now that A is 4, since we changed it, you can see, you might notice actually that now we have 2 polygons. We have one that we don't care about, and we have a completely new polygon from 0, 1, 2, 3, 4, and back that has our point of interest. But we don't know that yet because we should imagine that we're kind of the computer here. And so B is still the same, and we use this again, and we say, okay, 4 plus 1 divided by 2, ceiling, that's 3. So we take this temporary vector, and we ask, let's ask on both sides. Let's say if we first ask, is it to the right? Well, it's not to the right. So in that case, B would move up here. This would become B. If we ask, is it to the left first? Well, it is to the left. B would still move up here because there's no reason to search over here then. If it was on the right, then we would just move A over here. And so we discard the index, or change the index to be 3 then. And so you might notice now that we have a triangle, and that's important because that's a base case. And in particular, it's constant time to determine whether there's a point inside of a triangle. Right? It only has 3 sides. You only ask it 3 questions. Is it to the left of each of these vectors in a counterclockwise fashion? And so asking and answering the question of whether a point is inside some triangle ABC is always constant time. And so here, since the distance between indices is 3, or sorry, 1, we stop and we merely check if the point is inside the polygon. For P it is, for P prime it is not. Right, because we can just, based on the ordering, because it's sorted, formulate this triangle and ask the question. And so if we get a little bit more rigorous with this, we kind of have the input here. We use the same concept. We start with a boundary, maximum and minimum, and we make a sort of a constant vector here from the pivot point to the point in question in order to formulate our determinants. And we make the other vectors, which are from the pivot point to the max, pivot point to the minimum, same thing as A and B, and make the determinants. And so this is not true for the first iteration, and this is true for any basically garbage points that are just way out there that you can easily determine, as we just demonstrated, are not in the polygon. Now, we use the same formula, and so we take a sort of a temporary index and set it to the midpoint of the maximum and minimum, and recalculate the determinant using this new vector. And so if it's on one side or the other, we move either the maximum or minimum. And we move it, you'll notice that we move it by the amount of the midpoint, which is cutting it in half over and over. And we do the same thing before we go to the next iteration with the maximum. So you're sort of getting 2 iterations within the loop before the loop repeats. And so to give a rough sketch, you'll notice basically everything here is constant time except for the loop. And the loop only it only terminates when the distance between the two is 1. Now that's sort of related to proof of correctness, which is slightly more gritty, but I wouldn't say not straightforward. But let's just focus on what the time complexity looks like here. So basically what you're given is a search space n, and this max and min are needed to sort of terminate. So basically let's just, in the worst case, get as many iterations as possible, and we start off with max being n, and let's say this is not 0 base, so min is 2. And so remember that the formula is max plus min over 2. And so in the beginning, if it goes through as many iterations as possible, what's going to happen is you're going to get, for the first iteration of max, n over 2, n plus 2 over 2, the ceiling. Now, the thing about this is that if the value is odd, what's going to happen is it's going to be n plus 2 if it's odd. If it's not odd, it's going to be, or I should say n over 2, n over 2 plus 1 if it's even. But you'll notice that if you go through a few iterations, these switch so that in relation to max p, when it gets to the next decision, it's going to switch over and it's going to be 1 and 2. And so it just kind of switches from 1 and 2 and adds those constants over and over. So those constants don't really matter that much. And so what you're actually left with, well, let's say for max b, which can, and you can pick whether min or max, which one is going to be modified. It's basically the same. It's essentially the same. So it doesn't really matter, but let's just say that it's even, so that we'll make it easy on ourselves. And this will be n over 2. This is the new n, basically. This is the new search space maximum. And so this plus 2, the min, which hasn't been modified yet. And so if we take this, what we have is, we have n over 4 plus 1/2 plus 1, or 3 over 2. And because the ceiling, well, let's just suppose that this is this comes out to even, then what's going to happen is this is going to be n over 4 plus 2, right? So, and if it's not an, if it's somehow odd, well, then you get a 1/2 here, and that cancels out the fraction. But again, it doesn't really matter. You'll notice this is a 2 again, so it just goes from 1 to 2. It doesn't really grow. Not in well, certainly it's just constant, of course, but it just sort of switches. So we can just totally ignore that and notice that the first change of the capacity is n over 2, and the second is n over 4 within one iteration. And so if we suppose this for k iterations, let's say, then for the iteration k plus 1, you'll get this. And the thing is, for the k plus, well, this is for k iterations is 2 to the k, and of course 2 to the k plus 1, and this is for k plus 1 iterations, I should say. And you'll notice that actually this is just uh, 2 to the power of k times 1/2. The same thing for this, except it's times 1/4. So the constants don't really matter, and what's happening is that you're dividing the search space up to k times, or k plus 1 times, again, just ignore the constant. The point being is that this, through induction, it's easily demonstrated that this keeps going. So basically what happens is, given a search space of n, this search space is divided into 2 to the k, a fraction 2 to the k of it. And so this is k iterations. So if we take the log of both sides, remember that this drops because you take the log of 2 to the m for any m, it'll just equal m. So taking the log of 2 to the k is just k. So k iterations gives us log of n. And that's the dominant complexity because everything else is constant time. So it's pretty evident that this is a logarithmic algorithm for determining whether a point is in a polygon. And just to show kind of the meaningfulness behind this is that if you have like a polygon with like 10,000 points, okay, and you start the algorithm, the pivots, and you have a point somewhere, assuming it's just the average case, the normal case, the first vector you take is n over 2, so you've discarded 5,000 points already. And you do that over and over, and you'll see how useful logarithmic complexity is.